Welcome, everyone. I'm Gus Dowd, and I'm going to review a paper titled Groundwater Level Observations in 250,000 Coastal U.S. Wells Reveal Scope of Potential Seawater Intrusion by Scott Jazenko and colleagues, published in Nature Communications in 2020. In this paper, it's a groundwater elevation analysis conducted in the United States, and it provides us with a national scale evaluation of where groundwater levels lie below sea level, a condition that significantly increases the vulnerability to seawater intrusion. So a little background. Coastal aquifers supply drinking water to tens of millions of people in the United States. The aquifers, they're naturally protected from seawater intrusion because fresh water, typically, it flows seaward and creates a hydraulic barrier that prevents denser salt water from migrating inland. But because of large-scale groundwater pumping and sea level rise, and maybe some other things, it's been weakened. The seaward gradient has been weakened in some regions here. So this paper states that seawater intrusion is not just a local issue. It's a global concern. And although the seawater intrusion has been documented for more than a century, most studies have been limited to local or regional scales. And no comprehensive assessment has existed to evaluate where coastal groundwater systems are losing hydraulic head nationally. And prior to this work, our understanding relied heavily on just modeling studies, historic case studies, or site-specific monitoring networks. And there's been no national scale observation-based determination of where groundwater levels are already below sea level. And so no continuous picture of where landward hydraulic gradients have developed. And without this information, engineers, water managers, they can't identify where the areas that need to be looked at and mitigated. And this paper talks about seawater intrusion. It tends to be non-linear and slow to reverse. So once seawater moves into an aquifer, it requires significant recharge, sometimes like decades, a person's lifetime, to restore protective freshwater gradient. And that's why early detections of declining groundwater levels is important to us. And they also say that the groundwater elevation relative to sea level acts as a first order diagnostic indicator of vulnerability in terms of saltwater intrusion. And they also mention that sea level rise further reduces the hydraulic gradient that protects the fresh water. And what that means is that even modest pumping may cause increased vulnerability to some of these coastal areas. And that reinforces the need for systematic monitoring of national scale and national scale understanding of groundwater head conditions. So the purpose of the study is to identify where groundwater levels along the United States coastline are already below sea level, right? Because these conditions create a landward hydraulic gradient that enables seawater intrusion. So what these authors did was assemble one of the largest groundwater data sets ever compiled for coastal regions of the United States. And this data set, it consisted of more than 250,000 wells located within 50 kilometers of the coastline. Only groundwater level measurements recorded after January of 2000 were included in this study because they wanted it to reflect the modern hydrologic stresses like pumping, population growth, and sea level rise. Also, for wells with multiple measurements, like monitor wells, the authors, they took a median groundwater elevation from all the post-2000 samples that were taken. And that approach reduced the influence of short-term fluctuations due to things like tides, seasonal pumping, and many other local recharge events. And that's a more stable representation of long-term hydraulic conditions. And also wells with insufficient metadata or questionable elevation references were excluded to maintain the data's integrity. To evaluate vulnerability, the authors compared groundwater elevations to mean sea level using consistent vertical datum. By determining whether each well's hydraulic head was above or below sea level, they identified potential zones where the natural seaward gradients were reversed. Next, the authors divided the entire United States coastline into 20-kilometer segments, each extending 10 kilometers inland. Within each one of these segments, they calculated the fraction of wells with groundwater levels below sea level. If more than half of the wells in the segment showed heads below sea level, the segment was classified as having a landward hydraulic gradient. The study also did a sensitivity analysis on the robustness of their results, and that included evaluating multiple inland distance thresholds, 5 kilometers, 10 kilometers, 20 kilometers, to see whether the patterns changed, and or separating wells by depth to determine whether the shallow versus deep aquifers exhibited different vulnerabilities. And what they found is the overall spatial results remained consistent across these tests. And that supports the reliability of their findings. So let's get into their study. So this figure, figure number 1 in the study, it shows locations of previous studies that have documented either submarine groundwater discharge or seawater intrusion. The green points on the map indicated locations where freshwater discharges into the ocean, and the red points represent locations where seawater intrusion or landward hydraulic gradients were shown. So around this map are conceptual diagrams showing examples of various hydrogeologic zones. In Puget Sound, on the left-hand side of the figure, it shows a steep terrain and abundant recharge maintain natural seaward gradient. And the next diagram shows Salinas Valley, and that shows that decades of pumping caused seawater to migrate several kilometers inland in both shallow and deep aquifers because of the shallow aquitard that we can see there in that diagram. And if you look closely at Los Angeles, you can see the map shows that injection barriers were put in, and they successfully raised groundwater heads enough to slow the saltwater intrusion. And then if we go to the right-hand side, Miami's Biscayne Bay aquifer shows intrusion worsening because of the shallow aquifer and canals that leak into that aquifer. And if we go up the page from there, we can see that Savannah and Cape May show how deep confined aquifers can also experience the piezometric levels below sea level. So if we take all these together, what this figure is emphasizing is that even though these locations are unique, the common denominator for intrusion is dropping groundwater heads. So in figure number 2 in the paper, it shows a continent-wide view of groundwater levels relative to sea level. Each point, and these points are very small on this map or this figure here, there's a lot of them, but each point represents a well within 50 kilometers of the coastline. And the color corresponds to its most recent measurement post-2000. Red points mark wells where groundwater lies more than 1 meter below sea level, and blue points represent wells above sea level. So we can see some clear hotspots here. Southern California, most of the Gulf Coast, and portions of the Atlantic coast. And then the 6 insets maps provide a 100 by 100 kilometer close-up of selected coastlines, showing, and it's an interpolated groundwater surface in a little more detail in those certain areas. So what this figure shows us is that tens of thousands of wells already show head near or below sea level. So figure 3 in this paper, it shows how groundwater levels change with distance as they go inland. Panel A, the top panel, shows the fraction of wells below sea level at various distances from the coast. The highest proportion occurs really close to the shoreline, and it decreases steadily as it goes inland. And panel B shows, underneath panel A, shows that more than half of all wells with groundwater below sea level are located within 10 kilometers of the coast. And I think the highlights really from this figure are that coastal wells are more vulnerable due to lower natural gradients. And the second takeaway, I think, is that pumping can cause inland wells to also be vulnerable and fall below sea level as well. Okay, so figure 4. It's a little bit of a busy figure, but it's very important in terms of this paper's analysis. So it shows a map of groundwater vulnerability along the entire U.S. coastline. What the authors did was they divided the shoreline into 20-kilometer segments, and each with a 10-kilometer inland buffer. And then they classified each segment based on whether more than half of the wells had groundwater levels below sea level. And segments with landward hydraulic gradient appear in orange, while those that still have a seaward gradient appear in blue. And if we look at the picture on the left-hand side, the Pacific coast, most of the segments are blue. And that reflects what we talked about in the first figure, is that the West Coast has a steep topography and stronger natural gradients. But there also is some vulnerable areas, and they occur in Monterey, Oxnard, and Los Angeles. And they all have a long history of groundwater overdraft. And then if we look on the bottom of the figure in the middle, the Gulf Coast, it shows the most widespread vulnerability with large stretches of orange segments from Texas to Florida. And what the paper kind of mentions that causes that is the low elevation, subsidence, and heavy pumping. And that contributes to the extensive below sea level head across that region. Then if we look at the east coast of the United States, it shows numerous vulnerable segments, especially near Miami, Savannah, Charleston, Myrtle Beach, and around the Chesapeake Bay. These areas have shallow, highly transmissive aquifers and strong pumping pressures. The authors tested different inland distances and well depths, and the overall patterns remained consistent, indicating that these vulnerability hotspots are robust across all their methods. So the next table from this paper, it really summarizes everything in numerical form, and it shows that across the lower 48 states, 26.9% of wells within 10 kilometers of the coast have groundwater levels below sea level, and 15.4% of coastline segments show landward gradients. And now, regionally, the West Coast is the least vulnerable, with only 2.4% of segments classified as at risk. And the Gulf Coast is significantly more vulnerable, with 22.6% of wells below sea level and 17.3% of segments at risk. And the East Coast shows the highest vulnerability overall, with nearly 35% of wells and 18.4% of segments falling below sea level. And so I think what this table highlights is the vast difference in vulnerability between the three U.S. coasts. So then I just want to go into some of the findings. So what this study does is it shows us a widespread evidence of groundwater heads dropping below sea level. The patterns are more extensive than I think was known previously, and when looked at on a national scale, I think it becomes fairly clear that coastal aquifers in a lot of regions are losing their protective freshwater head, and that makes them more vulnerable to seawater intrusion. And these findings underscore the need for proactive groundwater monitoring and management strategies across the country. So uh, if we want to kind of summarize the hydrogeologic implications of the study, the authors uh, they emphasize that many U.S. coastal aquifers already have groundwater levels below sea level. And that means that landward gradients have already developed because seawater intrusion is slow to reverse. The priority must be prevention rather than remediation. And one major implication in that coastal region, it needs groundwater level targets that maintain heads above sea level. And in many of these vulnerable basins, especially along the Gulf Coast and Atlantic coast, even small declines could trigger widespread intrusion. And water levels will need to be actively raised to establish the protective seaward gradient. The study also kind of highlights that we need managed aquifer recharge, which is capturing stormwater and using spreading basins to implement aquifer storage and recovery, and it can help rebuild hydraulic head in both shallow and deep aquifers. And the authors say that reducing pumping near the coast rather than across the basin can significantly reduce landward gradients. And another implication is the need for denser or more frequent groundwater monitoring, particularly in the areas where heads fluctuate rapidly during pumping or drought. And continuous or automated monitoring would help managers intervene before salinity becomes irreversible. The authors also mentioned that we must account for sea level rise, which will continue to reduce the hydraulic gradient even without increased pumping. And protecting coastal aquifers will require coordinated regional planning and adaptive management. So, what are the implications? The study highlights several key management strategies: reducing groundwater withdrawals, enhancing managed aquifer recharge, expanding monitor well networks, and implementing injection barriers where they can, and maintaining hydraulic heads above sea level is very important in preventing irreversible seawater intrusion. So the authors did mention in this paper some of the limitations that they had. They noted that some wells only had single measurements. The digital elevation models had some uncertainty to them, and well locations were imperfect. and they weren't always accurate. And also, the study identifies the conditions for intrusion and not salinity itself. But they did run sensitivity tests, and they found that their results remained robust. So, just to conclude here, the study did show that around 15% of the U.S. coastline already exhibits landward gradients, with the highest vulnerability along the east and Gulf coasts. And nationally, patterns reveal in this study that highlight urgent needs for monitoring, regulation, and sustainable groundwater management. The findings offer a, a pretty data-driven foundation for anticipating and mitigating seawater intrusion across the United States. And I thought this was a particularly meaningful paper to review, and I enjoyed reading it. Thank you very much.